The phrase redox, which is our last type of reaction that we're going to look at today, is not new to you. You studied redox last year. When you studied reduction oxidation, the facts on this first slide that you already copied, this is just the first slide of the presentation. The vocab there is what you covered. In a nutshell, it wasn't hard to understand. Redox stands for reduction oxidation. And in a redox reaction, you were in charge of tracking the movement of electrons. There was a reaction, there was reactants, there was products, and when you compared the charges of the reactants to the products, you could tell who had grabbed more electrons, who had gotten rid of electrons by comparing their charge. That opening slide takes a look at vocab, oxidation, reduction, oxidizing agents, reducing agents. And those are important, and the basic skill, the honors skill of finding those values is in AP, but we're going to do that in Unit 12. That'll be at the very end of the year. Since we're doing reactions, and we've been looking through these different reactions, there's a different way that College Board wants you to be able to analyze a redox reaction. I want you to look at that top reaction that you wrote down. All right, we're now looking at this page. And what I'm saying is I want you to look at this reaction here. It's a redox reaction. However, it's breaking a rule of nature. Somebody tell me why. She said there's no H on the other side. There's an entire element missing. Do you see how there's hydrogen on the left and on the right? So we know that can't happen. So here's what this is. Listen, this is a little different. If I was a redox expert, let's say that my job was to work in the lab on redox reactions for like 12 straight hours. And I was going to be looking at these different reactions and I wanted to focus on the things that were moving electrons around. It would make sense for me to find a way to focus just on the items in the reaction that were taking place in the redox. If there were other things like water and stuff that make the science right, but it didn't matter for what I was going to do for the next 12 hours, if you were like, hey, I have a way you could ignore that part, I'd be like, awesome, I want to ignore that part. I just want to look at the part, like in that reaction, that is the redox part. Then that would be a good deal, and that's what scientists do. The reason that redox reaction looks weird, looks like you're missing a whole thing, is because some of the items in the reaction aren't shown. There's other items like water and hydrogen ion and stuff that makes it correct chemistry like you've learned, but it's inconsequential for someone that is only studying redox. So in other words, yeah, it is a wrong reaction. What I need you to be able to do is look at one of these redox reactions that has dropped out some of the important information and be able to put it back in. And that's what those steps are. I want to turn this focused redox incorrect reaction into the whole reaction so that that H that you're missing on the right isn't missing anymore. And I'm going to show you the steps to help figure out the missing parts. So have those rules in front of you. All right, I don't have a sheet of the rules, but you should have copied a bunch of rules on how to do these half reactions. And I'm not going to read them verbatim. I'm going to paraphrase from my brain, but you'll be able to follow along with me. So again, be patient with yourself. The first one is always a bit rough. All right, we're going to do this top one. All right, so we're just focusing here. All right, doing the top one on that slide I recently showed. Step one, from your rules, say split the redox reaction into half reactions. Now, this skill is really just an eyeballing skill. Here's what's going to happen. One of the reactants is going to have more in common with one of the products than the other product. And then, of course, the other reactant will have more in common with, well, the one you didn't select first. So what I'm saying is if you look at our first problem here, I would say that the permanganate ion here has more in common with the manganese. And if you can't see it right away, then look at the other one, and you'll see that that second item, the oxalic acid, definitely has more in common with the CO2, if you just kind of trace elements, right? So write this with me. One of my half reactions is going to be that permanganate ion, while the other one, and that will and I'm going to connect that to the manganese. The other half reaction, I'll pick the other reactant, is going to be the oxalic acid. And it's got stuff in common with the carbon dioxide. You'll notice I'm not writing the states of matter because they're inconsequential for anything we're doing today. It's the best chemistry to always write them, but you're going to already run out of room on your paper because you didn't plan properly. None of us do for this, but the states of matter are going to be unhelpful for us. Now, if you're sitting there and you're like, I don't even know that I can do what you just did. Again, I mean, maybe it takes a little bit of practice, but you can definitely tell that these have more in common than these do, or that these have nothing in common as these do. So it's that part's not designed to be difficult. For the next steps 2 through 5, I'm gonna compartmentalize. I'm gonna do this one 2 through 5, and then I'll rewind and do this one 2 through 5. It's the best way to think about it. So let's just focus on the top half reaction first. Step 2 says add coefficients to balance anything you can. Now, this might confuse you at first, but there's nothing we can add coefficients for here. How many manganeses are there right there? And how many are there right there? Yeah, it's 1 and 1. That's balanced, right? The charges don't have anything to do with balancing. You've been balancing equations long enough to know that. There's 1 manganese on each side. Hooray, that's what we want. Now, I know this is where things look really messed up because we're totally missing oxygen, but a coefficient won't fix that. I can't put a coefficient anywhere over here to make there be enough oxygen. So step 2 for the top reaction will be skipped. And now if you're worried and you're thinking, oh, I will never know when to skip it. Well, if you want to cheat ahead, I'm not going to, but if you look at the second one, some of y'all can see how there is a coefficient that would help us get started on the second one for some of the stuff. Whatever, I'm going to do that in a little bit. We're going to skip step 2 for the top half reaction. Step 3 says if you need to fix oxygens, then add water. If you have an oxygen problem, add water. Do you see how we have an oxygen problem? So I'm going to add water to the side that would fix our problem. But I don't just want to add water. I want to fix the oxygen problem. How many oxygens are there right there? So let's make there be. Now there's 4 over there. So yeah, I created the oxygen that I needed in the right amount using a coefficient. Just going right down the steps, even though this feels very foreign, it'll all make sense by the end of the period. Step 4 says if you have a hydrogen problem, add hydrogen ion. Do we have a hydrogen problem? Well, now we do, right? We created a hydrogen problem. There's no H's over there. So it says add hydrogen ion. So let's go to this side and add hydrogen ion. I told you wouldn't have the right amount of space. I don't know how to tell you the right way to do it, though. If I gave you guidance, it would just mess up a different person. How many of those ions do we need, though? That's not the right amount. What? 8. Right? See the 8 hydrogens? 8 hydrogens. All right, now, if you're sitting there and you're like, this is stupid, like, where's this even coming from? Like, what are you doing? You can't just, you're not God. But we're not creating new stuff, all right? We're not saying, oh, no, we'll add some hydrogen. What we're doing is these steps are a teaching process that chemists have come up with to just let you figure out what's missing. This water over there, those 4 waters, it was always there, all right? We didn't add it. We drew it on the board. But using these steps that are being provided from just a teaching perspective, we're discovering that it's there, even though it was always there. So I don't want you to think, oh, we're just doing this high-tech stuff. Man, we're just adding. No, we're not. We're uncovering the fact that it was always there, but the redox expert was ignoring its presence. All right. Step 5. Am I on 5? I don't really learn it that way. Okay. Step 5. This is something you've never done. Step 5 says balance the charge. We've never had to worry about balancing the charge before, but it's easy. Let me show you. Look at the reactant side. If you were to combine all of the reactant charges, what would the overall charge be? It would be 7 plus. Very good. All right. If you take 8 pluses and combine it with 1 minus, integer would be plus 7. Now, this green number I'm writing is not chemistry. I mean, you should probably write it so you can see it, but it doesn't go there or anything. I'm just showing you my thoughts. I'm thinking reactants are plus 7. What am I thinking about the products? What are the overall charge over there? Plus 2. And how did she get plus 2? Well, there's 1 plus 2, and there's 4 neutrals. Neutrals have no effect. There's my current charge. Are you with me? Now, we're still on number 5, right? Step 5. It says that we need to balance the charge with electrons. What charge do electrons have? Negative, which means if we're going to start adding electrons, it's going to make numbers go down. So when I choose a side that I'm going to focus on, because I want those green numbers that I'm just thinking about, not really writing, to be the same, I'm going to focus on the side with the larger number so that my electrons will knock it down to the other number. In other words, I want the 7 to become a 2. How many electrons would it take to make that arrangement? Now y'all are writing over the holes in the paper. Good teacher. Yeah, 5 electrons. All right, if you add 5 negatives to positive 7, it becomes positive 2. I don't know the best way to help you think about it, but you should know how to do that. All right, get rid of my thoughts. And hey, I've gotten somewhere with the top reaction. We're feeling good. Let's go to the other half reaction. Now we're going to rewind our steps because we weren't tracking it. So let's go back to step 2. But let's look at this reaction. Step 2 says add coefficients if they'll help. They will, as I've already previewed. What could we put to help this? A 2. Yeah, if you put a 2 right there, it fixes the carbons and the oxygens. Do you see it? And that was step 2. This time we didn't skip it. So there's never a confusion. Do I skip a step this time? Just if it's necessary, do it. If it's not, don't. Like watch what's about to happen to step 3. Step 3 says if you have an oxygen problem, add water. Do we have an oxygen problem? No. Our oxygens are 4 and 4. So don't add water, even though you did it on the other one. Just track carefully where you are. Step 4 says if you have a hydrogen problem, add hydrogen ion. All right, remember, we don't add water to fix hydrogen, right? So don't get those mixed up. Where should I add the hydrogen ion? Yeah, it's just to the side that doesn't have the hydrogen. So I'm going to add hydrogen ion, but I'm going to add 2 of them because I'm going to balance it as I fix it. Step 4. 4? Where am I? I'm sorry. Is it 4 or 5 for the charge? 5. Okay. Step 5, of course. I learned it in different steps, so I always get messed up because I found that these ones are clearer than the ones I learned off of, but then the numbers are all checked out. Step 5, we need to find the overall charge. All right, somebody shout out. Just shout out. What's the charge of the left? 0 or neutral. Those are both right because it's 1 neutral. Somebody shout out. What's the charge on the right? Plus 2. All right, there's 2 neutral, 2 pluses, plus 2. Who got questions? Should we suffer in silence? It's fun. Where are we going to add the electrons to fix it? On the right. If I get 2 minuses there, it'll drop to 0. You say so true? You want to come say that to the camera? You can. This is it. This is my forever video. I'm giving you choice. You come say hi, no? All right, come here. I'd like to welcome my assistant teacher, and he's going to take it from here.
Oh, hi guys.
You did really well. All right, so we've gotten to the same stage in each half reaction, right? And you see there's more steps. We're not done. But I compartmentalized. Hooray. We are getting close to remember what we're doing. It's important to me that you know. We are figuring out what is left out of the more targeted, the more focused redox reaction, right? We're finding the stuff that was always there. They just weren't showing it because they were lazy or whatever. Redox experts. Rule 6 says that the electrons from the two half reactions have to be present in the same amount. You have to have the same number of them. You see how there's 5 there and 2 there? They have to be the same number, and we're going to fix it. The way we do that is by multiplying entire reactions to change the coefficient. You see how they're all balanced right now? 5 to 8 to 1 to 1 to 4 is the balanced reaction up there. If I multiplied all of them by 20, all the coefficients by 20, would it still be balanced? Yes, right? As long as you change all 5 of those coefficients by the same factor, it would still be a balanced equation. So it would still be the same reaction. What I'm saying is I need these to be the same number. So what I'm going to do is multiply each of them to get the lowest common multiple, which between 2 and 5 is what? 10. So then what do I need to multiply the top reaction by? We're trying to get a 10 there. So let's multiply that whole reaction by 2. Every coefficient will give me a 10, a 16, a 2, a 2, and an 8. Still balanced. Same reaction, but 10 electrons.
And at least 6 lines on your paper.
Or buy a new spiral, she said, I guess. What should we multiply the bottom one by? Yeah, by 5. Remember, 10 electrons is the target. What? All right, so we're going to get a 5, and we're going to get a bunch of 10s. We okay? Getting there. We're almost to all the missing stuff. Finally, we're going to combine these back together. And when we do, we'll have the same reaction, but with the left out items. Now, when we combine them, though, a little trickier. Anything that replicates in the top half reaction and the bottom half reaction is going to cancel out, right? So it's kind of spectator ion-ish. But watch carefully because there's a little twist in just a moment. But here, look at the electrons. What are the electrons going to do? They're going to totally cancel, right? They're the exact same amount. Hey, guess what? That's always going to happen, right? But we made that happen on purpose, right? So we know that the electron count in every single example is always going to cancel out because of the previous step. But look at the hydrogens, the ions. Do you see how the H pluses replicate, but in different amounts? I want you to think of this kind of the way you think of protons and electrons canceling out their charge, all right? If I've got 10 in one hand and 16 in the other hand, when I go to merge them together, well, the lower number, all 10 of the 10 will disappear, which will cancel out with 10 of the 16 up top, leaving 6, right? So all 10, or rather the smaller number, will completely disappear. And the larger number will be kind of a leftover situation. So we lost all 10, taking away 10 of those, which leaves me with 6 H pluses. And down here in purple is the beginning of my answer, right? Because remember, we're just combining the leftovers together and then we're done. So right now, the leftovers are going to be 6 of the hydrogens. Does anything else replicate top and bottom? Nothing does. So now I'm going to take all the reactants and just list them. I'm going to take all the products and list them. Watch. All right, so I already did the H's. There's 2 MnO4s. Still reactants, there's 5 of the oxalic acids. All right, so I listed all the reactants. Now I'm going to switch over to the products. There's 2 manganese ions, 8 waters, and 10 carbon dioxides.
Does it matter which one, like what order you put in?
It's an addition problem, so no. Just make sure reactants stay reactants and products stay products. Now, some students would consider this skill to be loco, but I hope that you're doing okay. So the purple is the answer. You'll notice the original redox reaction is still present, but now I can see all of the items that were left off. Now, if you're looking at the steps you wrote and you're thinking, wait a second, there's a bonus step at the bottom that we didn't do. I would like to point out that this first problem is mentioned to be acidic, which is the reason this is the final answer. You're not missing anything. But the pH environment is a big deal here because you see those H pluses that are in our answer? You know that H plus is characteristic of acids, right? It's the reason that acids start with H. All right, that was the last year skill. I don't know if I've said exactly that, but yeah, hydrogen ion is a characteristic of acidic environments, which is why we're done, because that's an acidic environment. The problem is that these steps that we're using to get here are always going to create an acidic environment. Sometimes it's not acidic, which is why we have another example. Are you ready? We're about to draw a bunch of cards, so I want you to get comfy. No, sir. Was that the guest host that yawned? Okay, sorry, just came from the corner. If you look at the next example, you'll see there's a basic environment solution, but it being basic only changes something at the very end. Everything else is the exact same. So let's get some practice and let's get more comfortable with these steps. All right, so we're on the bottom one now. Let's go talk to some people. Cluster 5, seat 1. It is pretty awesome. Step 1 says to separate the reaction into 2 half reactions. Can you just give me one of the half reactions? Perfect. He said BrO3 minus, because he wouldn't leave off the charge, is going to create bromide. Everybody okay with that being one of the obvious connections between reactant and product? Which means the other one is going to be the iron 2 yields iron 3. All right, so the other one will be iron 2 yields iron 3. There's our 2 half reactions. All right. So let's do the top one first. All right, we'll focus on him. Let's go over to cluster 4, C5. Hey, Mr. Allen. What coefficients would help us right now? He said none for the first one. Would any help us for the bottom one? The answer is no. Now, if I hadn't showed you the balancing of charges, he would have said no right away because he's learned for years that if there's one iron and one iron, then you're balanced. But the water's got a little muddy in your brain there, so keep them separate, all right? It's okay if the charges are different, right? You fix that with electrons. We're not doing that right now. If I'm asking for coefficients, well, one bromine, balanced. One oxygen, messed up, different problem. One iron, balanced. Rule 2 will not help us on either of our half reactions. Okay, we're going to do just the top now. If I call on you, it's the top equation only. Step 3 says if you have an oxygen problem, add water. So let's go over to cluster 6, Aspen, it's you. Aspen, do I need to add water, and if so, where? Perfect, you can pass Aspen. She said we're going to add water over here. And that fixes my oxygen problem, but keep in mind that there's 3 of them.
Excuse me?
Yes.
Is it Firewind?
Yes.
Please send her to attendance.
She is on her way.
Thank you.
I called you that for a whole semester, so it's all right. The next step says if you have a hydrogen problem, add ion. Let's go.
Okay, I see it. I see.
We good?
Yes, we're good.
We good. Let's go to cluster 1. Oh, now it's going to come get you. Watch this. C1. Yeah, it's weird. It's weird how the cards do that. Help me fix my, or do we have a hydrogen problem?
Yeah.
So where am I going to add it?
On the left side, we're gonna add 6H+5.
Perfect. We all right? Y'all are being very non-questioning. I'm a rock star at this, right? Maybe. Okay. Let's go over to cluster 3. C2. Hey, 3-2. I just want to find my charges. Can you tell me the overall charge of the reactants? Perfect. And what about the products? It's perfect. Great job. 6 pluses and 1 minus is +5. 1 minus is -1. Yeah? Remember, the green is not a part of any answer. Just a thought. Let's go over to cluster 1. C4. Hey, 1-4. How should I fix the charges? What would you do?
On the right, or no, on the left side, you would add 4.
Try that number one more time.
No, on the left side.
No, the left side is correct, but 4 is wrong. I need to get from 5 all the way down to -1, not +1. Yes, you're good. Yeah. So, yeah, 5 down to 0 is 5 to -1 is another one, so 6 moves. We okay? Cool. I finished the top one. I'm not going to draw cards for the bottom one because it's kind of fun and fast. We already said no coefficient. What do we need to do to the oxygens? Nothing. There are none. What do I need to do to the hydrogens? Right? And when I say there are none, I mean there's not one on a side, right? If there was one on a side, we'd have an issue. But if they don't exist, we're not going to introduce them or anything. Now, the charges, though, are off. But this one's kind of easy to see. It's like +2 and +3. So where should I add the electron? Anybody? Yeah, they're right. So +3 minus 1 is +2. Yeah? All right, let's go back and draw some cards. Let's go over to cluster 5. Ooh, already got one of them earlier. C4, Aspen, it's you. What do I need to multiply by to make the electrons the same in both reactions? What will the magic number be? 6. Yeah, and this time I only have to multiply one of them, right? Last time we had to multiply both, but do whatever is the simplest. I just need to multiply the bottom one by 6. All right. So we'll get a 6 and a 6, and that's when the demons show up. So we'll do the rest of the class in the dark. Turn red. See, it always works. Hi. We okay? The next step says to cancel out like items as you combine into the answer. What is like this time? Yeah, it's just the electrons this time, right? And the electrons will always do that. All right, but nothing else copies. So now focus in. I don't want you to think, because remember, the basic solution thing is going to cause us a major issue in a second. But let's bring everything together first, like we did last time, and we'll get an almost answer. All right, so starting with my reactants, it looks like I'd write small if I were you. We have the hydrogen ions, we have the bromate ion, we've got the 6 iron 2s. All right, we've got bromide along with some water, and then some iron 3. Does it look okay to you? Now, if it were an acidic environment, we would be done. The purple would be the answer, and we would feel pretty good about ourselves. But I like it when you feel bad. These H pluses that are hanging out here make it look acidic. It is the way we have it written. We need to change it to being basic. How do we get rid of the H pluses? What substance will neutralize H plus? OH minus hydroxide. All right. Every time you have an H plus and an OH minus, they essentially neutralize. But neutralize doesn't mean remove. It means what is formed when you do neutralization. Water. Makes water. So when we fix this here in a second, it's not going to remove anything right away. It's going to create H2O. So now I'm at that next bonus step. If you're still following along steps, you have this next thing written down. Those 6 H pluses need to go. To neutralize them, I need an equal amount of OH minuses. So let's add 6 OH minuses. Now, there's a couple things we need to think about here. First off, we worked really hard to create that balanced equation, and then we unbalanced it. So the thing that would make the most sense then is if you add it to the left side and you want it to stay balanced, let's also add to the right. Right? Now again, if there's a part of your brain sitting there being like, wait, can we do that? Remember, these are just teaching steps to figure out the mystery of what was left out. This is not you just dropping in OH minuses on the product side in the lab. All right, we are figuring out, like a detective, what the overall reaction is. But we're balanced again. The equation is still balanced. So whenever we do this fix, you're going to do it to both sides is the first thing to know. But here's the other thing. You see the 6 OH minus and the 6 H pluses? That's stupid. We wouldn't write it like that. Because as I just said, every time you have one of those and one of those, you form water. So don't write this. Just watch for a second. I don't want to write it like that. I want to write it like this, but don't do it yet. Because that expression and that expression are the same thing, right? We're just thinking this. You with me? But if we suddenly have water over here, which we do, Look over at the product side. You see that water? This is going to rewind us a few steps just for a second to the whole cancel out thing, which is annoying. But if I have 3 waters in one hand and 6 waters in the other hand, and I do that canceling thing like we did earlier, what am I going to be left with? 3 waters on the heavier side. In other words, those 3 waters are going to totally cancel, which is going to turn this number into a 3 because 3 of them canceled out of the 6, and now we're done. So what's left? Well, there's 3 waters. All right, which attributed to those. All right, then we've got our bromate ion. Got our 6 ions. Bromide. 6 iron 3s. 6 hydroxides. The brown is the final final. Do you see how it's a basic environment now? Do you see the hydroxide floating around? Hydroxide is the basic characteristic, and our process created it there, which it was always there in the final answer. I have some good news for you. Well, I'm done with you.